Welcome back. In the last video, we looked at the gamma function, and the reason we did that is so that in this video we can start talking about the gamma distribution. So if you recall, the gamma function is denoted by the Greek letter gamma. And the gamma function evaluated at alpha is given by the integral from 0 to infinity t to the alpha minus 1 e to the minus t dt, where alpha is greater than 0. Now, in this equation, if I divide both sides by gamma of alpha, then we end up with 1 on the left. And since on the right hand side we are integrating with respect to t, not alpha, we can put, when we divide by gamma of alpha, we can put that inside the integral. So we get 1 is equal to the integral from 0 to infinity t to the alpha minus 1 e to the minus t divided by gamma of alpha dt. So as a result, since the integrand is non-negative and integrates to 1 from 0 to infinity, then the integrand can be thought of as a density function. More precisely, if I define this to be, if I define a function which is, if I define a function of t which is equal to this integrand, when t is greater than 0 and 0 otherwise, then that's going to be a density function. So, then if x is a random variable with the density function fx of x equal to x to the alpha minus 1 e to the minus x divided by gamma of alpha for x greater than 0, then we say that x has gamma distribution with parameter alpha comma 1, and we denote this by using this notation. This is known as the standard gamma distribution. So the standard gamma distribution with the parameter alpha and 1 is the distribution with this specific PDF. Okay, so now what we're going to do is we're going to put or introduce a scaling factor for this gamma distribution. That we will generalize this a little bit more. So let's say that x has x has the standard gamma distribution, and let's set y to be a random variable that is equal to x over lambda, or in other words, x is equal to lambda y. If we do that, then what would be the PDF of y? Well, the PDF of y would be the PDF of x multiplied by dx dy, and then that's equal to, so dx dy here, obviously dx dy would be lambda, and then fx of x being lambda y in the standard gamma density, we replace x by lambda y, so lambda y to the alpha minus 1 e to the minus lambda y over gamma of alpha. That's what we have here, and then we are multiplying by dx dy, which is lambda. So this is when y is positive. So if I set y to be x over lambda, or x is equal to lambda y, then the PDF of y is given by this function. Now, to be more precise, how do I come up with this PDF of y? If you want, I just gave you this formula without telling you where that came from. But one of the tricks that we applied in another video before is that we first calculate the CDF of y. So the CDF of y evaluated at y, that's the probability that y is less than y, but y is x over lambda, so that's less than y, and then x is less than lambda y. So the probability that x is less than lambda y, that's exactly the CDF of x evaluated at lambda y. So now I take the derivative of fy of y, which will be the PDF of y, and then if I take the derivative of fx of lambda y with respect to y, then we would be getting the derivative of the outside is here. You see the outside function here is fx, which would be the PDF fx evaluated at lambda y, and then multiplied by the derivative of lambda y, which is lambda. And then you just plug that in the PDF for x, and then this is exactly what we get. Okay, so then we say that the x has a gamma distribution with parameters alpha lambda if its PDF is given by this formula that lambda times lambda x, fx of x is lambda x to the alpha minus 1 e to the minus lambda x divided by gamma of alpha for x greater than 0 and 0 otherwise. So that's the PDF for the gamma distribution with the parameters alpha and lambda. The again in place of so I wrote this in terms of y before, so now I'm just writing that in terms of x. Obviously this new x here is taking the place of the previous y. Now the expected value or the mean value of x when x has gamma distribution with parameters alpha and lambda is given by alpha divided by lambda, and the variance is given by alpha divided by lambda squared. When we have a gamma distribution with the parameters alpha and lambda, then the alpha here is called the shape parameter. Lambda is the scale parameter. So here is a graph for the same lambda value but for different alpha values. So when alpha is 1, what happens is that when alpha is 1, you pretty much end up with the exponential distribution. So when alpha is 1, you pretty much get the exponential distribution here, and then when alpha is 2 or 3, you get this other two graphs for the PDF function. The N-Arling distribution is pretty much the gamma distribution, except that instead of alpha, we use a positive integer n here. And so if I use n here instead of alpha, then we get what is called the N-Arling distribution. And again, the exponential distribution can be obtained from the gamma by simply picking the shape parameter alpha to be 1. Now the gamma distribution with the parameters n and lambda arises as the distribution of the amount of time until a total of n arrivals occur, like n emails or earthquakes occur. So we can think of one application of the gamma distribution is exactly this, that we can think if x has a gamma distribution with parameters n and lambda, then we can think of that as the distribution of amount of time until a total of n arrivals occur. So to explain that a little bit more, let's say we have this we have this process evolving where we are observing arrivals of some events like emails or earthquakes. And so let's say x1 is the x1 is the time until the first arrival. X2 is the time, is the amount of time it takes to get the second arrival since the first arrival, and so on. So each x1, x2, xn, these are inter-arrival times. So again, x2 is the time between the first and the second arrival, and so on. So let's assume that each of these variables has exponential distribution with parameter lambda, and they are all independent. So they are IID with exponential distribution. Then one can show or prove easily that if I take x to be the sum of these variables x1 plus x2 plus dot dot xn, then notice that x is the amount of time until a total of n arrival occurs. So then the distribution of x can be shown to be given by the gamma distribution with parameter n and lambda. So this could be proved. So if we have x's which are IID with exponential distributions, then the sum of n of the first n of these variables would have gamma distribution with parameters n and lambda. Okay, so that's all I want to say on the gamma distribution.